Today we will discuss context free grammar and ambiguity. Context free grammar is defined as a quadruple V, sigma, R, and S, where V is a set of non terminal symbols, sigma is a set of terminals where intersection of V and sigma should be phi. That means there should not be same symbol in set V and set sigma. R is set of rules. S is start symbol. Set of rules can be mapped from V to closure of union of V and sigma. Consider one example of context-free grammar where S, A and B are non-terminal symbols, 0 and 1 are terminal symbols, and set of rules, or we can say productions, are like this, where S derives A derives 1A, A is terminated with 1, B derives 0B, B is terminated with 0. The strings generated by this grammar are n number of ones and followed by n number of zeros. These rules are used to generate strings. If A tells to B is a rule, then the sentential form xay is derived to the next sentential form xby. So we can say that xay derivates xby. If like this, from the starting symbol S, we could reach to a sentential form T, then we can say that T is derived from S after n derivations. A given string X is member of closure of sigma can be generated from the given grammar if it gets derived from the starting symbol S of that grammar. So, like this, we can define the language over the grammar. L of G is nothing but the set of strings which are member of sigma star and derived from S. Consider one more example of grammar and some strings. The given grammar contains only one variable S, two terminals 0 and 1, and two productions or rules. We can say that null is a member of the given language because S derives null. Similarly, 0, 1 is member of given language. Like this, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, like this up to we can have a general definition. 0 raised to n, 1 raised to n is in L of G because we can derive such types of strings from S. So the language is defined like this, where n should be greater than or equal to 0. A context-free language L is a context-free if there exists a context-free grammar G such that L is equal to L of G. So if we are having a context-free grammar, then the corresponding language is context-free language. The strings which are member of the given grammar can be derived either in leftmost derivation or in rightmost derivation process. So in leftmost derivation, the leftmost variable is replaced always, and in rightmost derivation the rightmost variable is replaced always. Means the rule is applied for the rightmost derivation here, and in leftmost derivation the production rule is applied for leftmost variable. Both derivations have same parse tree. So a parse tree is nothing but a tree which contains S as the root, and the leaf nodes are the string symbols, and intermediate nodes are generated by using the rules applied. So like this, if S tells to S, BS is the rule applied, then S has the three child nodes S, B, S. And if the rule applied is S tells to A, then S parent node will have A as a child node. And at the leaf node, all terminal symbols are present. A parse tree has a unique leftmost and a unique rightmost derivation. But for some strings, the case is not true. From the parse tree, we cannot identify which type of production is applied. If some strings have different parse trees, then what will happen? Here are some examples. We cannot judge the derivations are either leftmost or rightmost because the sentential form contains only single non-terminal. In some examples like this, we cannot judge whether it is a leftmost or rightmost because there is no any sequence of variable to be replaced. The variables are replaced in any random order. If a string has multiple leftmost derivations, like this, consider a grammar. S tells to A and S tells to SBS. For a given string A, B, A, B, A, we are having two leftmost derivations. If we change the order of production rules to be applied, then we get two different leftmost derivations and two different parse trees. This creates confusion or ambiguity. We can define such string as an ambiguous string for a given grammar because it has more than one parse tree. A grammar is ambiguous if it generates an ambiguous string. It is hard to test whether a particular grammar is ambiguous or not. But if we could find a string which has multiple parse trees for leftmost derivation, then we can say that the given string and corresponding grammar is ambiguous. As an exercise, you can test whether the grammar is ambiguous and whether you can convert this particular grammar into an unambiguous grammar or not. We will see in next lecture how to convert a given grammar into an unambiguous grammar. So the conclusion is a string is ambiguous for a grammar if it has more than one parse tree for a given leftmost derivation, or same definition can be applied for rightmost derivation as well. Consider some examples as an exercise at home. You can take some strings which has multiple leftmost derivations and justify the given grammar is ambiguous. One of the example is explained here. Consider the string of well-formedness of parentheses from the given grammar. This particular string can be generated in two different ways. Both derivations are leftmost derivations and two different parse trees are generated for the same string. So this particular string is ambiguous and the grammar is also ambiguous. We need unambiguous grammars to manage programming language semantics. Consider one more example which has two different meanings for the same string if it generates two different parse trees. The algebraic equation a minus b minus c can be treated as a minus in bracket b minus c for one parse tree and a minus in bracket minus c for the other parse tree, and it could generate wrong results. In next class, we will discuss think, pair, share activity for the problem of dangling else. You can consider one of the string as a program fragment given here to generate multiple parse trees and leftmost derivations.